So in part D, we are told the amplitude of these oscillations and the mass of the particle. In part 1, we need to calculate the total energy of P. So for total energy, we have the very nice formula that E total is equal to 1/2 m omega squared maximum displacement squared. So we need to calculate the angular frequency. Angular frequency is simply 2 pi times f. We know the frequency is 210 hertz. So if we plug it in, we will get 1.319 times 10 to the 3 radians per second, or simply per second. And so the total energy, we have to just plug into this formula. We know the maximum displacement is 4.2 times 10 to the minus 3 meters. We know the mass. Everything is in SI units, so all we have to do is plug it in. And then we will get 2.8 times 10 to the minus 5 joules. And then in part D2, we need to calculate the displacement of P when its kinetic energy is equal to its potential energy. So when they are both equal to each other, we know that the total energy is kinetic plus potential, but if they are equal to each other, it means that they're both halfway to the total energy. So kinetic energy is half of total energy and potential energy is half of total energy. As when we add those two together, we will get total energy and they are equal to each other. So we can say that the potential energy is simply 1/2 m omega squared x squared, and this is going to be 1/2 of the total energy, which is 1/2 m omega squared x0 squared. So what we can do here is cancel pretty much everything out, and we will find that x squared is equal to 1/2 maximum amplitude squared, and so the displacement x is going to be the square root of, well, 1 over root 2 times x0, our maximum displacement of 4.2 millimeters. This will give us a displacement of 3 millimeters.